All right, so the plan today is to wrap up lecture series number 14. So we continue. Okay, so I don't know if people had a chance to go through an example that I don't know if it was Chileshe or Anita who was asking this question, but somebody wanted to find out how exactly we go about evaluating negative 21 base 10 plus 6 base 10. This is the same process here, right? Assuming you are given this sort of scenario, could be the exam or something, or I don't know when or where or who would ask you this question, but the process you go through is the same. Assuming you're told to encode or to evaluate this using two's complement, what you do is you go through a systematic process of, first of all, converting the individual numbers. So you convert negative 21 base 10 into binary, right? Using two's complement, same process we went through, the rules, right? And then you convert positive 6 base 10 to binary using the rules associated with two's complement, and then you perform binary addition. Right. Remember, you must remember here, irrespective of whether you're dealing with a negative number or a positive number, if you have an expression that requires you to evaluate the result of combining a positive and negative number, a positive and a positive number, you can view both of those different problems, or in fact, a negative number and negative number, as an addition problem, right? So it's either you're adding two negative numbers, you're adding a positive number and a negative number, and you're adding, of course, two positive numbers, right? So in this case, what we're doing is we are adding a negative number and a positive number, right? So we can do this actually, I guess, for the benefit of those of you that didn't get a chance to work through this. Let me see if I can just squeeze it or push it on top there and then try and minimize this so that we're able to see what we're doing here. All right, so what we're saying is the first process is we need to first of all convert the different numbers, right? So we have negative 21, that's 10. I guess it'd be nice if we do what instead what Molim is teaching us in spreadsheet applications, we just use a subscript here. Oops, the subscript, I don't know why it's not working, but nope. Wow, subscripts are not working today, which is quite sad. Who cares? Okay, so negative 21, there's 10. I don't know what's happening to my LibreOffice Calc instance today. So we first of all convert negative 21 to binary, right, using two's complement. And we know the rules, right? The first thing we need to do is we get the one's complement equivalent of the number, and then we'll add one, right? So we convert negative 21 to binary. First thing we do is we, I guess we can do this stepwise, right? So that we are able to tie the different pieces together. In fact, this is part of the reason why I'm doing this. So we'll convert positive 21 first to binary, right? 20 to 21 is 5, remainder 1. Sorry, this is 10, right? Remainder 1. 2 into 10 is 5, remainder 0. 3 into 5 is 2. The remainder is, sorry, yeah, 2. Sorry. Yes, it's 2, the remainder is 1. 2 into 2, the answer is 0. Sorry, it's 1, the remainder is 0. 2 into 1, the answer is 0, and the remainder is 1, right? So we have 1, 0, 1. The answer is 1, 0. Just do that here. 1, 0, 1, 0, 1, right? I don't know if I'm still sleepy here, but let's just confirm 21 to binary 1, 0, 1, 0, 1, right? Yeah, I don't think I'm sleepy here. Woke up a long time ago. But anyways, so we've converted positive 21 to binary, right? But remember, for us to get one's complement, what we'll need to do is we need to invert the bits, right? So we're saying positive 21 is 1, 0, 1, 0, 1. To get the one's complement of this, right? So just that. This is, I'll just explicitly do that so that people know exactly what we're doing. So we get the binary equivalent of positive 21, and then the ones complement. Jeez, how can we? Anyway, one's complement of this is just flipping the bits, right? So we get 0, 1, 0, 1, 0, right? And then 2's complement. 2's complement is going to be the result of adding 1 here, right? So we say this resulting value here plus 1, right? For us to get 2's complement. Remember the rules? If we're dealing with a negative number, we're dealing with negative 21. So we get 1's complement of negative 21, which is here. For us to get 2's complement, we just add a 1, right? So effectively what we're saying is the 2's complement is just going to be equal to 1 and this is, I guess we can say this is a carry, and then this is a result anyway. 0 and 1 is 1, and then the 0. I mean, you know the drill, don't have to go through this. So 0 and 1 is 1. 1 and nothing is 1. 0 and nothing is 0. 1 and nothing is 1. 0 and nothing is 0. And then forgot something here. And this is where you have to be careful, by the way, because when you have a positive number and you're trying to use 1's complement, you must remember that this thing here, like so. All right, so we come up with 1 0 1 0 1 0 1 0 1 1 1 2, yeah, 1 2 3 4 5 6, right? All right, so we have our 2's complement equivalent, which is this here, right? 1's complement is right here, right? So we're saying negative 21 when represented using 2's complement, this is the answer. If the answer required you to represent it using 1's complement, you'd have what we have here in row number 2 here, this part that's highlighted in yellow. There we go. So we have negative 21. What we have to do now is get positive 6, because remember what we're evaluating is negative 21 plus 6 base 10, right? Getting 6 is pretty trivial. We go through the same process of repeatedly dividing, whatever method you want to use. I prefer repeated dividing. We repeatedly divide 6 by 2. So 2 into 6 is 3, remainder 0. 2 into 3 is 1, remainder 1. 2 into 1 is 0, remainder 1, right? So we realize that, in fact, our positive 6 is equal to 110, right? 110. And here's the thing, right? Getting the 1's complement of a positive number is just a positive number. So 1's complement is this, right? Getting a 2's complement of a positive number is just that number, right? So it's still going to be 101, 110, sorry, right? So we have our value here converted to converted to 1's complement and 2's complement. And this is the answer we have here. I'll just highlight the 1's complement in yellow and the 2's complement in green so that you see the result, right? All right, so we have both numbers encoded using 2's complement. The next step is we simply perform binary addition, because this is a negative number, negative 21. This is positive 6. For us to evaluate negative 21 plus 6, all we do is we add the negative number and the positive number. So we come here, and what we're going to say is we'll perform binary addition normally, right, as we normally would. So we have 1 0 1 0 1 1, like so. Just going to squish this so that it's more legible, I suppose. All right. And then we will add this to 0, 1, 1, 0, right? Right, so we perform binary addition, and the answer here is going to be 1. So 1 and 0 is, okay, let's do this normally, I guess, so that people understand here. We have our carry bit, and then we'll have our, so we'll have our, yeah, let me just move it somewhere here, just in case there's an overflow. We have our carry bit, and then we have the result here. 1 and 1 gives us 1. The remainder is 0. 1, 1, and 0 gives us 0. The remainder is 1. 1, 0, 1, 1 gives us 0. The remainder is 1. 1, 0, 1 gives us 0. The remainder is 1. 0, nothing, and 1 gives us 1. 1 and nothing gives us 1, right? So what we are saying here, ladies and gentlemen, is that the answer of evaluating negative 21 and positive 6, or the expression negative 1 plus 6, negative 21 base 10 plus 6 base 10, when evaluated using 2's complement, gives us 1, 1, 0, 0, 0, 1. Right? Right. And so here's the thing. I mean, you could probably, maybe we could take advantage of this and probably do this here. I'm just going to highlight this in red so that people see this. What we could do is, we can already see here that because the most significant bit or the leftmost bit is a 1, then the answer is a negative, right? So the question to ask is, how exactly do we prove that this is, how exactly do we go from what we've gotten here to a decimal equivalent, just so we can prove this, right? And by the way, there's nothing like using a calculator now, right? The calculator will give you a wrong number here. But so here's the thing here. Going in the reverse, you remember the rules? Any volunteers on how we go from 2's complement encoded binary value to a decimal equivalent? Because what we want to do here, right, is we want to check to see if we will be able to get negative 21 plus 6. Oh, come on. Okay, 6 minus 21. We want to see if we'll be able to get negative 15. Do you understand this? Hello, are you still there?
Yes, sir.
Yeah, so we want to check. Are we going to get, how do we get to negative 15 here? What do we do?
We find the decimal equivalence of 1, 0, 0, 0, 1.
Are you really sure that's what we do? What are the rules? What are the rules when we are, could you mute your microphone? What are the rules when we are converting? You must think about the rules here. We discussed the rules. We said when you are converting a binary encoded number, where the hell is that thing? When you're converting the binary, when you're converting a binary encoded number, the rules, you add 1 and then you flip the bits, you flip the bits and then you add 1. Are you forgetting that thing? Where is that thing here? No. Did we not discuss this? I thought we discussed this. My God. There we go. Are you forgetting these rules here? Rule number 2. When you have a 2's complement encoded binary number, what you do is you follow these rules here. Flip the bits, add 1, convert to binary, and then place a negative number. So this is what we're supposed to do here. Flip the bits, 0, 1, 1, 1, 0, 0. Add 1. Jesus. Sorry. Add 1, 1. What happens when you add 1 here? 1. Gee, I don't know, maybe we want us to do it the normal way where you have the carry bit here and the result. G, not E, carry C. Carry bit and the result here, right? 0 and 1 is 1, remainder 0. 1 and 0 is 1, remainder 0. 1 and 0 is 1, remainder 0. 1 and 0 is 1, remainder 0. 0 and nothing is just 0. 0 and nothing is just going to be 0 here, right? So we have this number here now, right? What do we do next? We've flipped the bits, we've added 1. What do we do next? We convert this thing here into decimal now, right? This is your ones place, twos place, fours place, eights place, right? This is what we're interested in on anyway. So it would be 8 plus 4. There's something we haven't done, right? 12. Yeah, so 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. I guess you want me to use Excel like Mr. Molim said. Can we use the sum function, please? Well, I mean, everybody knows how to use the sum function. I just used it just now. So we have the answer here, right? They taught you this in spreadsheet applications, 15. Once we get 15 as a final step, we include the negative here because this is a negative number. We know it's a negative number because the original 2's complement encoded value had a 1 on the most significant bit. So this is negative 15 in effect. Do you understand this?
Sir.
Yeah, so let's remember this, right? So I don't know who asked this question. We're saying, sir, how can we evaluate negative, I don't know, maybe it was from a book or something, negative 26 plus 6, right? Now we know, right? Your toddler brother or sister will probably tell you, oh, negative 21 plus 6 is, well, it can't, I guess, but they'll tell you it's negative 15, and we just prove that it's negative 15, right? So this is what you should probably be doing if you are if you come across such a question in the exam, and you will, by the way, in the exam and the test 2, which is on the 6th of November. You want to be able to prove these things, right? Let's say you evaluate an expression and you come up with your 2's complement encoded result. You need to be able to prove that this is correct. You won't do this using the calculator, right? Surprise, surprise, not there. Right now, if you knew how to write MIPS code, you probably use it using MIPS or something, and then because MIPS it uses 2's complement encode the numbers or something. Is this making sense? Is our discussion of 2's complement, does this make sense now? I mean, I thought we'd kind of wrap up on this note where I showcase the example or question that somebody asked last time we met, I guess the day before yesterday or something. Any thoughts? Okay, no thoughts, no questions. Great. If that's the case, then let's proceed, right? So now that we've discussed all these 3 different techniques, right? Yes, hi.
Hello. There's a question that I came across. It's like, what are the disadvantages, or like what are the benefits of the 3 methods that we just used? Sign magnitude, 1's complement, and 2's complement.
What are the disadvantages?
The advantages and disadvantages.
I don't know. I thought we discussed its advantages and the disadvantages. You want to think about its advantages and the disadvantages from the perspective of having more than 1 0. Errors resulting from subtraction, right? Yeah, so you want to think about the disadvantages from this perspective here, right? Range of values as well. Range of values that you end up, range of values of integers. You have to think about this, and we look at this notion of range of values here, right? The fact that if you're dealing with sign magnitude, you know that the range of values is just going to be 1 less because of the sign here, right? So yeah, I mean, you can think of the disadvantages and advantages from this perspective here. The fact that some of the methods, specifically sign magnitude and 1's complement, will have 2 zeros, right? Some of the methods will result in illogical answers or solutions that result when you're performing a subtraction operation, right? Remember the case where we said we look at -5 + 5, for instance. We expect to see a 0 here, but there's no 0, right? You get a completely different answer here. Yeah, and then think of it from the perspective of the range of values of integers. But the range of values of the integers is somewhat linked to this notion of having more than 1 0, because if you have more than 1 0, what that means is that the range of values of integers that you're going to be working with is going to be slightly less, right? Because one of them is occupied by the additional 0, right? You'd have like a +0 and a -0. Who does that? -0 and +0. All right, but let's see if I hope that helps address your question here. We briefly touch on this question you just asked as we wrap up, and you see just now where we do a comparison of the different methods, right? There we go. Yeah. So I hope by the time we're done with this, Thelma would have answered your question. If not, maybe we can talk a little bit more about it. But let's look at this summary, right? View here of the different methods that we discussed, right? What you will notice, if we just look at the range of integers from -5 to +5, for instance, left to right on our number system here, you realize that the representation of the positive numbers is pretty much the same, irrespective of the type of encoding you're using, right? Why? Because in all these different instances, the leftmost bit or the most significant bit is used as a sign, and everything else is a size, right? Also, we realize from the rules and the rules associated with 1's complement and 2's complement, because there's no rule for sign magnitude. The only rule that's there is that you just use the leftmost bit as a sign bit. That's the only rule that's there. 0 for positive, 1 for negative, right? But for 1's complement, we went a step further and said what we do is if we have a positive number, then we just convert it to binary as we normally would. If we have a negative number, then we convert the to binary the equivalent of that negative number, and then we flip the bits, right? So if we're dealing with 1, for instance, here, 1's complement, yeah? If we're dealing with 1, what we do is we convert +1 to binary. Sorry about that. We'll convert +1 to binary, which is here, 0, 0, 0, 1. And then we flip the bits. And then we'll flip the bits, and then we'll have 1, 1, 1, 0. Simple rule, right? For 2's complement, what we do is we, I don't know why I left the gap here, but what we do, but what we do is we get the 1's complement of the equivalent of the negative number, and then we add 1, right? And you can see here that +1 is still going to be the same for 2's complement, right? 0, 0, 0, 1, but the -1 is going to be 1's complement +1. So we get the 1's complement, which is 1, 1, 1, 0, and then we add 1, and then we have 1, 1, 1, 1, right? So this is your -1 there. Does this make sense? And also, I mean, if you start performing your subtraction operations here by just adding the positive and negative numbers, you notice that as you're working with sign magnitude here, you get very strange things here. But when you're working with 2's complement, for instance, if we have +1 and -1, we add 0, 0, 0, 0, 1, and 1, 1, 1, 1, 1, you notice that we'll be able to get a 0, right? So again, just to try and grab a little bit of salt here, 1, 0, 0, 0, 1, and this is +1, and then 4 1s, right? 1, 1, 1, 1. What we're saying is that if we perform an addition here, because one of them is negative, one of them is positive, we should be able to get what we expect. 1 and 1 is 0, carry 1. 0, 1, 1 is 0, carry 1. 0, 1, 1 is 0, carry 1. 0, 1, 1 is 0, carry 1. What do we do when we have an overflow? Throw away.
Discard.
Beautiful.
Discard
Thank you very much. Yes, and then so we get a 0, right? But if we were to start evaluating sign magnitude, for instance, here, we say we add +1 here, which is 0, 0, 0, 0, 1, and -1 here, which is 1001. Observe what happens, right? We come here, we'll say we have 0, 0, 0, 1, and then we have 1, 0, 0, 1, we have 1, 0, 0, 1. Observe what happens, right? This is an addition operation, obviously. Come on, addition operation. 1, this is our carry bit, I guess. This is going to be our carry bit. This will be carry bit, and the result here, it's an addition operation. Addition operation. 1 and 1 gives us 0, carry 1. 0, 0, 1 gives us 1, carry 0. 0, 0, 0, 0, 0 gives us 0, carry 0. 0, 1, 0 gives us 1, carry 0. And then this is it. And this is the thing here. If you look at this result, 1, 1, 0, 1, 0. This is sign magnitude. We know that if this is sign magnitude, if we were to do the reverse from a sign magnitude encoded binary number back to decimal, what we do is we go through a process where we first of all realize that only these 3 bits signify the magnitude, right? This is a sign bit. The sign bit of 1 tells us that this is a negative number, right? The magnitude is, this is 1's place, 2's place, so it's -2 here. But +1 minus 1 is not -2, right? It's supposed to be 0. All right. This makes sense, I hope, right? Any thoughts about these different methods here before we briefly talk about this idea of integer overflow, right? Even though we have introduced it, but it'd be worth talking about it.
So,
yes, sir.
I don't know if I came late, but the example that has been discussed on slide number 366, I was going through it. I noticed something that I didn't really understand on 366.
366.
710 minus 310.
Yes.
Yes, when you're working out the solutions, there's something that I didn't really understand on how you evaluated one of the additions.
Okay, which part did you not understand? I mean, we're saying +7. You want us to go through?
Just show the whole solution, and then I'll let you know. Yeah, just there. The first one was 1 plus, since the first column was a +7, and the second one was a -3 equivalent of the positive, and then you flip the bits to have the one in the third row.
Yep.
So you added 1 plus 0 to give us 1. But the second one, I don't know how you were supposed to add the 1 plus 0, but you just indicated 0 instead of 1. I don't know how. I missed something there.
Which second one did we say we added a 0?
From the right, the first one.
Yeah, there's a number of rights. Do you want to tell me which column exactly you're referring to?
When you start the addition process with the first bit, from the right going to the left.
Which part? Let me just. Okay, I thought this was. Which row are you referring to here? This is row number 1. Which row are you referring to?
So I'm talking about the addition of the whole thing.
Yeah, I'm trying to make sense of where exactly the issue you have an issue with. So assume this is row number 1. This is row number 2. Which row are you referring to? This is row number 3. This is row number.
The addition should be row number 1 and row number 3, not so.
No.
1 and
the addition of, no, it's row number 4. So here's the thing, right? Negative, we can always do this again, right? So positive, maybe we did make a mistake, but here's the thing, right? This is +7 in 2's complement, is that agreed?
Yes, sir.
Okay. -3 in 2's complement is this row you have at the end here, where you first of all get the 1's complement. How do you get the 1's complement? You first of all convert +3 to binary, which is second row here, 000000011, and then you flip the bits, 1 1 1 1 1 1 1 0 0, and then you add 1. So we're adding 1 to this third row here. When we add 1, we have 1, 1, 1, 1, 1, 1, 0, 1. And then what we do as the final step is we are adding this row here and this row here.
Oh yeah, that's why I missed it when you added the one. The first.
Yeah, maybe we should have marked this differently. I don't know. I mean, but it's just a visual, just to showcase to you how this was being done or something. So you must have used a spreadsheet or something. I don't know. But yeah, so what you want to do is, I guess I was doing this stepwise, but maybe I should have color coded them differently if it was confusing. So we're adding this and the 2's complement equivalent, because for us to get the 2's complement equivalent of -3, we go through 3 steps. Or you can view them as one step really, 1's complement and you add 1, right? Or 3 steps where you first of all convert in this case, if you're converting -3 to 2's complement, you first of all, step number 1, convert the positive equivalent of -3 to binary. So essentially get the binary equivalent of +3. Second step, you flip the bits of the binary equivalent of +3, right? Which is step number 2 here. Third step, you add 1, right? And then you get this. And then you say 1 and 1 is 0, remember 1 and 1 is 0, and then you go ahead and it says. All right, great questions there. Any other, we must talk about, there's a quiz on Tuesday, we must talk about what is confusing us, if there's anything confusing you. Anything else that, yes?
So you only discard the carry bit when you're using 2's complement?
Yes. When you're using 1's complement, what do we do? Can you take us?
We add the bits.
Beautiful. So when you're using 1's complement, what you do is you compensate. When you have a carry bit, you add it to the least significant bit or the rightmost bit. When you're using 2's complement, you discard the carry bit or the overflow. The carry bit can be viewed as an overflow, right? And the overflow is linked to how you're encoding the numbers, representation, bit representation you're using. So if it's the 2-bit representation or 8-bit representation, maybe 16-bit representation for half a word or something, 32-bit representation for a word, then you discard, right? It turns out it's quite important. You will realize that this idea of range of numbers becomes really important once you discuss 2010 next year, right? When you're dealing with different types of data types, numeric data types like integers, doubles, and floating-point numbers, for instance. All right. Unless there are any other questions, then I guess we'll proceed. Any thoughts? Any other thoughts or things that are a bit iffy or confusing anywhere? No. Okay. All right. So it turns out that as you are performing these arithmetic operations using binary numbers, sometimes you might be faced with a situation where you have an overflow, right? And an overflow typically occurs when you have slightly more things to store than you have available space, right? So in this case, we are looking at how you're storing these bits, right? So assuming you are working with, let's say, a 2-bit register in MIPS, for instance, and you perform an operation that results in a relatively large number that cannot be represented using 32 bits, you have an overflow, right? The example I have here is a situation where you want to evaluate, let's say, 2 base 10 and 254 base 10, right? Assuming, think about this for a second, assuming that you're storing this value, assuming that you're dealing with unsigned integers, just positive numbers, right? You will notice that if you're using 8-bit representation, you remember that formula we said the range of values using 8-bit representation. If it's positive numbers, it's going to be 0. Do you remember? First of all, do you remember that the total number of integers, positive integers that can be represented using 8-bit representation is 2 to the power 8. You remember this discussion?
Yes.
Yeah, I remember. I don't know about you. So we can store 256 integers. Now, if these 256 integers are positive integers, what we further said was that the range of integers that we can represent here are going to be from 0 all the way up to 2 to the power 8, in brackets, minus 1. So effectively, the integers that can be represented using 8-bit representation, positive integers, is going to be 0 up to 2 to the power 8 is 256 minus 1, which is 255. Do you understand here? If you evaluate 254 plus 254 plus 2, you will get 256, right? 254, 255, 256. 256 cannot be represented in here, so you have an overflow. This is what we're talking about here. This is the idea behind an overflow, right? An overflow would have occurred. Now, overflows are handled differently, really. In certain instances, the answer will be truncated. In some instances, depending on the application will signal an error or something, right? So it will be treated as an exception. And this is how MIPS behaves, actually, right? So if you were to think of some of the issues that might happen here, this is what I was talking about, some programs will generate an exception or an error to let you know that, that there's a problem with the computation, right? The storage location or storage space is not just sufficient to hold the resulting value, right? So you get an exception. Usually in a user-friendly manner, right? And these are things you typically think about as a program, and you'll be taught how to do this in 2010, by the way. There's a part of 2010 called exception handling, if you will, right? So you look at different scenarios of different exceptions that can occur and exactly how you handle them, right? If you're going to use Java, you'll be introduced to something, the notion, the idea behind the try and except block or something, where you test to see if an exception is going to occur, and then you handle the exception, right? All right. So something else you can do is you can design your program in such a way that your result will be truncated, right? So you truncate the result, but the problem with truncating why did I do this? It's program without ME. Now, if you're dealing with monitoring and evaluation, then this would be a program, right? It's program with spelling. So this is the thing. Another way of handling the overflow is you truncate the result, right? So instead of generating an error, the result will be truncated, and so you get a wrong answer. What we mean by truncating the result is observe. If we wanted to evaluate 2 plus 254, you must now start thinking of what we're doing here in binary. I won't waste time to look at to convert 254 we could, but 254 in binary, I'll use the calculator, right? I'll cheat a little here. So 2, 4, 6, 7, 1, 2, 3, 4, 5, 6, 7. That's 256 with a 0 at the end. 256. And then we need to add 2, right? It's stupid, but we'll use the calculator just in case. 2, 1, 0, right? What we are saying, guys, is that observe. If we are saying we're using 8-bit representation, we have 1, 2, 3, 4, 5, 6, 7, 8. If we're using 8-bit representation, what we're saying is these numbers are going to be encoded like so, right? They'll be represented using 8 bits. If we add this, if we add 254 plus 2, what we end up with is a situation where, and this is our carry bit and the result here. 0 and 0 is 0, remember 0. 110 is 0, remember 1. 101 is 0, remember 1. 101 is 0, remainder 1, 0, remainder 1, 0, remainder 1, 0, remainder 1, 0, remainder 1. What we have here, this thing that's highlighted in yellow, is what we are calling an overflow. Why is it an overflow? Because if you were to add it here, if we were to add, and we can add it here, our answer is going to be 1, 0, 0, 0, 0, 0, 0. This thing that's highlighted in green, yeah, is represented using how many bits? 1,
9, sir.
yes, 9 bits. But we are saying we're supposed to encode this using 8-bit representation. Because the answer is represented using 9 bits, we have an overflow. This is what we're calling an overflow. An overflow can be treated differently. We could throw an exception here and signal to whoever is going to be using this program, right? Or if it's a program writing code, to say there is an overflow, an exception has occurred. An exception is something wrong, right? Or alternatively, what we can do is we can truncate the result. Truncating the result here will mean we discard. We discard anything beyond the 8 bits, meaning that our answer is going to be just these zeros because we'll throw away this 1. Now, because we are truncating and getting these zeros, then what we are saying is that the answer is 0. But think about this for a second. 254 plus 2 is not 0. It's supposed to be 256. We have truncated the result, and we have we've come up with an answer of 0. The 0 is what we are calling a logical error. It's something that does not make logical sense, right? Right? So this is what we're saying. So another thing we could do, an approach, is we truncate the result and we get the logical error, right? I mean, another workaround is you can add additional space. I mean, if you're privy to doing that, right, as a program or something, right? So implications of binary integer overflow here, if you have an overflow, right? Something to think about here. So just to try and exemplify things here, when we're dealing with MIPS, and I do apologize, we won't do this. We're going to get our hands dirty, but looking at the time, we won't really play around with MIPS to write simple programs in assembler here. But we'll just briefly introduce how we go about doing this, maybe in 1 or 2 sessions, maybe 3, I don't know. Right, so this is an example of an exception. You will notice here that I get an error to tell me to say, if in this case I was attempting to add, I don't know what I was adding here, but I was adding 0 to, let me just evaluate 65,000, right? I was adding 0 to 65,000, 65,000. So I was adding 0 to 65,000, and you will notice here, I don't know if you can see this, but you will notice that it's telling me to say, in 2's complement, I can only represent range of integers from negative 32,768 all the way up to 32,767. Because 65,000 is outside of this range, there's an overflow, so I get an error. I have an exception that comes my way. As a program, I'm writing this code, I get an exception. Right, this is what we're talking about here. I hope this kind of makes sense to people here. So I mean, again, just looking at signed integers here, range of numbers, we're talking about 0 to 55, 0 to 2 to the power 16 minus 1. If you're dealing with a word which is like 2 bits here, it would be 0 all the way up to 2 to the power 32 minus 1, right? These are the range of integers that you're working with. When you're working with signed integers here, and this is something that I'm talking about here, right? So when you're working with an unsigned, I always get confused signed and unsigned. Right? It's always like I'm talking about unsigned and I'm talking about signed. When I'm talking about signed, I'm talking about unsigned, but I'm talking about unsigned here. All right, so the formula for evaluating this, if you're dealing with unsigned integers, right, it's positive numbers, including 0 here. What we're saying is that this is the sort of formula we work with, right? 0, the range of integers you're going to represent is 0 all the way up to 2 to the power n minus 1. 2 to the power n minus 1, right? So you just plug in the values. If you're dealing with 16-bit representation, it would be 2 to the power 16, the answer minus 1, 0 up to that value. Right. I hope this is making sense. But if you're dealing with signed integers using signed magnitude, what we're saying is the formula we are working with here is positive or negative 2 to the power n minus 1 minus 1. Do you understand? And you got to think about this for a second, right? Think about this from the perspective of you having 2 zeros. You remember those 2 zeros, which is why you're saying the range of integers that you're going to be working with is positive or negative 2 to the power n minus 1 minus 1. Effectively, what we're saying, another way of looking at this is we're saying it's going to be positive, it's going to be negative 2 to the power n minus 1 minus 1, all the way up to positive 2 to the power n minus 1 minus 1, right? If we are working with 3-bit representation, for instance, yeah, 3-bit representation is the simplest to work with here. 3-bit representation means we will have how many numbers are we going to have here? 2 to the power, it's just 2 to the power. It's going to be up to 2 actually, right? Because we can only represent these numbers here. 0, 0, 0, 0, 0, 1, and 0, 1, 1. The positive numbers, right? Negative numbers is going to be 1, 0, 0, 1, 1, 0, 1. And the reason I'm doing this is I'm using a very small bit representation so that this idea of the range of integers sinks in, right? And this, I want to latch on to Thelma's question about what are its advantages and disadvantages here. 1, 0, 0, 1, and then we have 1, 1, 1. Right? So effectively what we're saying here is that we are representing 0, 1, 2, negative 0. This is really strange here. Negative 0, negative 1, and negative 2. If you count these, 1, 2, 3, 4, 5, 6, right? This is what we're saying here. For us to be able to derive this, the range, 0 or is it 0 all the way up to negative 2 here. Maybe we should have done it the other way around. Doesn't matter. So we'll follow the number line left to right. It doesn't matter. For us to get this range of numbers, what we're saying is we use this simple formula here. This. And we can prove this, right? We are saying the range of numbers is going to be negative. It's going to start from negative. The lowest number is going to be negative 2 to the power, it's 3-bit representation. It will be 2 to the power 3 superscript minus 1 minus 1. And effectively, what we have here as the lowest integer that can be represented using sign magnitude with 3-bit representation is going to be negative 2 to the power 2 minus 1. Right? Hey, are you still there?
Yes.
So, on illustration, sir.
Yes,
Yeah.
sir.
Just go back
Yes.
a bit. Illustration, the spreadsheet.
Just give me a second here. 3-bit representation. You don't have a 3 here though.
Yes. Oh. The 0, 1, 1. Isn't 2 supposed to be 0, 1, 0?
Sorry, isn't what?
Isn't 0 isn't 2 supposed to be 0, 1, 0?
Yes, it is. Thank you. Beautiful stuff. The smart kids from the block. Okay, yes, thank you. I was wondering where the formula is trying to. Thank you very much. And then in here as well, we have just do what Mr. Mwalim told us. We can insert, right? Right click. Are you enjoying 11, 10, 20? Boring course, but no, it's fine though. We can insert, right? Insert the row or something. So this is the thing here, right? Thank you very much. Beautiful. So if you look at this, for you to derive this range of values here, you just plug in this formula here. This is what I'm doing here. For us to get the lowest number, we just plug in the numbers and you notice that we have -3 here. as the lowest number. If you plug in the positive numbers, it's just like flipping the sign here. You have the positive and then you have positive 3. So what we're saying is that for us to get the range of numbers for sign magnitude, we just use this formula here. 2 to the power n minus 1 minus 1. 2 minus 1 is here. The other minus 1 is only superscript. The other one is just normal. And then we'll get this range here. 0, 1, 2, 3. Negative 0, 1, negative 1, negative 2, negative 3. Guys, is this making sense? I don't know. I suppose. All right. Okay. So I don't know if it's making sense. I don't know what the silence is all about here. So, but what about one's complement, right? Well, it turns out that when you're dealing with one's complement, remember, because of the fact that the problem with this 2 0 pair that, not 2, but pair is 2, with the 0 pair that we have, we use the same formula, right? As sign magnitude. So effectively what we're saying is with one's complement as well, because the 0 problem is still there, the range of integers that we're going to be working with is the same, essentially. So same formula, right? 2 to the power negative or positive 2 to the power n minus 1 minus 1. Yeah, so it doesn't matter whether you're told, oh, this is 64-bit representation. Who does that, right? Or 32-bit representation, 16-bit representation, or 8-bit representation, or a NIBO, right? 4-bit representation. You just plug in the numbers, right? But because with 2's complement, we have effectively gotten rid of the problem with the 0 pair, the formula that we work with is slightly different. Effectively, the range of integers that we're working with is going to be negative 2 to the power n minus 1 all the way up to positive 2 to the power n minus 1 minus 1. And the reason we don't have another minus 1 here, as opposed to when we compare this to sign magnitude and 1's complement, is because we've gotten rid of the negative 0. Negative 0 does not make sense, right? 2's complement gets rid of the negative 0. And so the range of values we're working with is going to be negative 2 to the power n minus 1 all the way up to positive 2 to the power n minus 1 minus 1, right? By the way, this is where MIPS, this QT stream is coming in here. If you remember, I'm just going to delete these annotations here. You see what it's telling you here, say, the error that it was telling me, the range of values is going to be negative 32,768 all the way up to positive 2,767. This is because of the minus 1. This is actually represented in 2's complement, and you can see this, right? Guys, you can work your way behind here by just and you can see that this is well, I'll leave it up to you to work. I'm looking at the time here. You can work backwards and try and see if you can identify the bit representation here. Can you? Like given this range, right? Anyway, maybe it doesn't matter anyway. But I was trying to say here that this range of values that we have here is 2's complement, effectively. Yeah? If you think about it. The positive value is 1 less than the negative value here. Yeah? All right. I'm so sorry that we didn't start data encoding. My hope was that we would use this session to start data encoding, but that's fine. We start tomorrow, right? If you want, maybe we can skip prayer day, but I don't want to be controversial. Say they forced us to go to school on day of prayer or something. Good luck praying here. So summary, I mean, we've done quite a bit here. We're done with lecture series number 14. We've done quite a bit here. We're playing around with essentially number systems. Even though our focus was on how a computer gets to represent data, which is 1s and 0s, we started off our discussion by really contextualizing this and looking at scenarios where number systems are used. And in fact, these are the different bases, right? Our focus of attention, of course, was hexadecimal and decimal for obvious reasons. We did discuss these reasons. At some stage, we latched on to what we discussed when we were looking at the Unix case study by highlighting the fact that the octal number system is the one that is, in fact, used when you're dealing with permissions. You remember this, right? This is the octal number system where we're saying the maximum, the maximum permission is 7777, right? The minimum is 0000. Think about this for a second. 0 through 7 is base 8, right? Octal number system. But And then we really went on and revised grade school type work. I don't know if it's grade 1 or kindergarten or something, where we are adding base 2, right? How do we add? How do we subtract? How do we multiply? How do we divide? And then we started looking at how a computer gets to actually represent these binary numbers. Now, again, you must remember here, we're abstracting this notion of representing binary numbers because effectively a computer does not store ones and zeros. You're looking at, we're abstracting the flow of electric current. That's what we're doing here. It's fine, we can look at the flow of electric current in terms of ones and zeros. So we looked at 3 different methods that have traditionally been used. I'm sure there's more methods out there. You want to look these things up if you're curious, right? So sign magnitude, 1's complement, and 2's complement. Your modern day computer encodes data using 2's complement, right? You'd have seen this using QT-SPIM, the simulator, MIP simulator, but because of time, I won't see this, but that's not an issue here. And then we just wrapped up by looking at you know, how exactly, what sort of the range of integers that can be used to represent values. I want to leave you with this here, right? When you're dealing with numbers, I want to leave you with our discussion today to think about this notion of, oh, I'm working with 32-bit registers, right? What range of numbers are you working with, right? It turns out, right, this is the range that you'll be working with here. Billion, right? Now, in some instances, you think, no, maybe the numbers that I would want represented will not fit, right? Maybe I want to be working with trillions or something. Slightly larger registers would solve this problem, like 64-bit register or something. You get to discuss some of these different things, like different data types that you get to work with, like floating point and doubles and floating point values or something. Are there any thoughts or questions with regards to lecture series or complaints with lecture series number 14? Was this fun? Was it fun to go back in history and relive grade 1 work with Miss Banda? Did you enjoy this? I did. I always enjoy this myself. Are you still there?
Yes, sir.
Yeah. Did you enjoy this?
It was cool.
Yeah. Well, it doesn't matter whether it was cool or not cool, right? Sadly, but it would have, I mean, I always strive to make it enjoyable, but it has to be done, right? It's a means to an end. All right. I'll see you tomorrow where we'll start lecture series number 15. Yes, sir.
It's okay. It's okay.
Okay.
It's okay. Yeah.
Great. Thanks a lot. I hope I was recording this, and yes, I was.
Are we having the class tomorrow or Sunday?
I'm sorry?
Are we having the class tomorrow or Sunday? You said they don't have about prayer day tomorrow or something like that.
No, prayer day is Sunday. According to my calendar, I don't know, correct me if I'm wrong, but I'm looking at my calendar. Prayer day is Sunday. How fitting, right? They say it's a sign from God that we must not have class, right? Because prayer day is on Sunday or something. It's Sunday, right?
Yes, sir. Yes, sir. Yes, sir.
Yeah. Guys, when I told you to use Google Calendar, you must use Google, when you look at software, you must use Google Calendar like Lighton does. I have the Zambian holidays here. I get to integrate them into my schedule, right? So if you look at the schedule here, so prayer day is on the 18th, right? Independence Day was on the 24th, apparently, right? Where's the 24th? It's Saturday. Oh, it's next week. Okay. Back-to-back holidays here. It doesn't matter. It's a Saturday anyway. Christmas Day is on the 25th. You should do what Lighton does, right? You integrate Christian holidays, in fact, even or something. All right. See you tomorrow, I guess. I don't know. Thank you. Enjoy and study for Tuesday quiz.
It's
All right. Good day.
all right. Good day. Good day. Good day. All right.